Usually when you get a medical diagnosis, it's pretty binary. You break your arm, the x-ray shows that stark, jagged white line across the bone, and the doctor just points at it.
Right, there it is. Broken. It's clean.
Exactly. It's super clean. But imagine you take that same x-ray machine and you point it at, I don't know, a human memory or a thought process. Suddenly, that machine is totally useless.
Yeah, the landscape gets murky real fast.
Right. And that exact feeling, staring at a diagnostic tool that suddenly makes absolutely no sense, is what happens when a developer tries to build an artificial brain on their laptop, and the system just starts hallucinating.
It is a terrifying moment for any coder.
Oh, I bet. So welcome back to our ongoing deep dive series. Today's journey is titled LangChain, Your Second Memory. We are picking right back up with our hero, developer Vitali, who is deep in the trenches of coding a universal document ingestion engine.
Which is a massive undertaking.
Huge. He's trying to turn his personal laptop into a perfect, completely private, local, retrieval augmented generation system. Basically a second brain.
And what makes Vitali's journey so compelling for anyone listening who wants to experiment with AI is that he isn't, renting time on a massive server farm in some corporate basement.
No, not at all.
He is completely constrained by standard, albeit powerful, consumer hardware.
Which makes the stakes so much higher. I mean, imagine you're Vitali for a second. You are operating on an AMD Ryzen AI 9 HX370 CPU.
A great chip, but still a laptop chip.
Right. You've got 32 gigabytes of system RAM, and you're running an NVIDIA RTX 4060 laptop GPU with exactly 8 gigabytes of VRAM.
And that 8 gigabyte ceiling is, well, it's the tiny box he has to fit a whole brain into.
Exactly. And the brain he's chosen for this local operation is Llama 3.1, specifically the 8 billion parameter model.
Which, to be fair, is arguably one of the most brilliant choices for local execution right now.
Oh, for sure.
But 8 billion parameters, or 8B models, they have very specific quirks, especially when you push them to their absolute limits.
And we are definitely pushing them today. Because if we look at the bigger picture here, building this second memory isn't just about dumping your files into a database and hoping the AI figures it out.
Not even close. It is this incredibly delicate, highly technical dance between how you vectorize the data on the way in and how you extract it on the way out.
Right. And often, what looks like a complete database failure or a terrifying AI hallucination is actually just a poorly optimized system prompt.
It's all in the prompt.
It really is.
Yeah.
So in our last deep dive into Vitali's setup, he conquered basic subtitle files. But today, the training wheels come completely off.
Oh, yeah. Things get real.
He is facing the final bosses of document ingestion. We're talking markdown files, raw Mermaid architecture diagrams, and the ultimate matrix trap Excel spreadsheets.
It is a serious gauntlet, and it starts with a fundamental problem that plagues almost every single RAG pipeline built today.
From amateur laptops to enterprise systems.
Right, exactly. And that problem is context pollution.
Yeah, I want to spend some time on this because the way this bug manifested was just wild. So Vitali tries to ingest a really simple markdown file, just a basic .md document.
Right, just a text file.
Yeah. And it contains a 24-item reference list of LangChain document loaders. He uploads it via his Python script. Then he asks his local Llama 3.1, right in his terminal, to show him that exact list.
A super simple request.
You would think. But the AI just completely loses its mind. It starts making up fake API components. It starts talking about OpenAI and Hugging Face.
Which aren't even in the document.
Not at all. And it just wildly repeats phrases from his old chat logs. It's a total mess. I mean, if you saw this on your screen, you'd think the database was totally corrupted.
You absolutely would. And what's fascinating here is the underlying mathematics of why that specific hallucination happens.
Okay, break it down for us.
So to understand it, we have to look at ChromaDB, which is the vector database Vitali is using under the hood. ChromaDB doesn't read text the way a human reads text. It doesn't look at words on a page. It uses mathematical semantic distance.
Okay, semantic distance.
Yeah, it takes a sentence and converts it into coordinates in a high-dimensional space.
I'm trying to visualize this. So instead of like a filing cabinet sorted alphabetically, it's more like a massive 3D grid where concepts that mean similar things are clustered physically closer together.
Exactly. But it's not just 3D, right? It's hundreds of dimensions. The embedding model evaluates the meaning of the words and plots them.
Got it.
So the word dog and the word puppy are mathematically very close together in this coordinate space, even though they share no letters.
Okay, that makes sense for concepts.
Yeah.
But why did it cause the hallucination with the markdown file?
Because of how Vitali structured his database initially, he mixed his actual ingested document files into the exact same vector pool as his old conversational chat logs.
Oh, no.
Yeah.
Yeah.
The logs where he previously typed things to the AI, like, give me the full list of LangChain document loaders.
Oh, I see where this is going.
So when he searches the database for the list, the database looks at his new prompt, calculates its mathematical coordinates, and searches for the closest match.
And mathematically, his previous questions were ranked as more relevant than the actual markdown file containing the answers.
Exactly.
Wait, I think I get this. If I walk into a library and I ask the librarian for an encyclopedia on LangChain, I expect the book.
Right.
But instead, the librarian hands me my own personal diary, open to the page where I wrote, "Dear Diary, I really want to learn about LangChain today."
Yes.
The librarian is just looking at the words and saying, look,
Yeah.
the semantic match is perfect.
That is exactly what is happening mechanically. The raw string queries from the user are triggering memory vectors instead of document vectors.
Wow.
The mathematical distance between his current prompt and his old prompts is incredibly short. They are practically sitting on top of each other in that high-dimensional space.
Right.
So ChromaDB grabs the diary, fills up the AI's limited context window with it, and hands it to Llama 3.1.
And Llama 3.1 looks at it, realizes there's no actual list of document loaders in this diary entry, but it still has a prompt to fulfill.
Exactly.
So it panics and just starts guessing based on its pre-trained weights from the internet. Hence the hallucinations about OpenAI and Hugging Face.
Precisely. It is operating perfectly based on the flawed context it was given.
That is so frustrating. So if I'm Vitali, I'm thinking, do I just delete all my chat logs? Like, do I have to choose between having documents or having a memory of our conversation?
Well, you don't have to choose, but you do have to organize. And Vitali implements a highly elegant fix in his vectorterminal.py script.
Okay, what does he do?
It's a concept we can call dual query isolated retrieval. Instead of throwing one wide search net into the database and hoping for the best, he refactors the code to execute two completely separate database queries.
How does he separate them?
Using Chroma metadata filters.
Right, because LangChain allows you to attach metadata dictionaries, basically little sticky notes, to every chunk of text before you save it.
Exactly. So every time he saves a document, he adds a sticky note saying source:document. Every time he saves a chat log, he adds a sticky note saying source:user_history.
Brilliant.
Now, when he searches for files, he uses a filter condition that says $NE:user_history.
And that NE stands for not equal to.
Right. This forces Chroma to strictly isolate the search to actual documents, completely ignoring the chat logs, regardless of how mathematically similar they are.
That's clever. It forces the librarian to only look in the nonfiction section.
Exactly. And then he runs a second, entirely separate query with the filter $EQ:user_history, meaning equal to user history.
So that pulls the conversational context.
Yes. He feeds both of these clean, isolated streams of data to the LLM separately, with strict instructions in the prompt on which one is the source of truth and which one is just memory.
Okay, problem solved. The librarian finally gives us the LangChain encyclopedia. We sit down to read it.
But wait.
Right, we open the encyclopedia and half the pages are ripped out.
Yeah, they're just gone.
Because even with this brilliant dual query fix, Llama only outputted the last few items of that 24-item list. Items 1 through 16 were just entirely missing.
And this raises a critical question about how we prepare data for an AI. We just solved the retrieval logic, but now we hit the chunk fragmentation issue.
Okay, explain chunk fragmentation.
When Vitali ingested that markdown file, he used a core LangChain utility class called the recursive character text splitter. And he had the chunk_size parameter set to 512 characters.
Walk me through that. Why 512 characters? That seems like a pretty standard default for most RAG tutorials you see online. It keeps the data bite-sized so you don't overwhelm the AI's context window, right?
It is standard, yes, but it's incredibly dangerous for structured lists.
Why is that?
Well, the text splitter's job is to take a massive document and break it down into smaller pieces for the vector database. It tries to split on paragraphs, then sentences, then words. But a list doesn't have standard paragraph breaks. So the splitter literally took his single 24-item list, hit that 512-character limit, and chopped the list with a meat cleaver into 3 completely separate mathematical vector chunks.
Oh, wow. So chunk 1 has items 1 through 8, chunk 2 has 9 through 16, and chunk 3 has 17 to 24.
Exactly. They are now 3 isolated islands of data. So when Vitally searched for the list, ChromaDB ran its mathematical similarity search. It found the chunk with items 17 through 24, decided it was highly relevant.
Because it matched the semantic search for the list.
Right. It handed it to the LLM, and the LLM accurately reported exactly what it saw. A list starting at item 17.
It's doing exactly what we told it to do again.
Yeah.
We slice the data too thin. The AI isn't hiding the rest of the list. It literally doesn't know it exists in that moment.
Yeah.
So how do you fix a fragmentation issue like that without just making the chunk size massive and blowing up your VRAM?
Vitally had to adjust the search depth during the retrieval phase, which in vector databases is commonly known as the k-value.
The k-value.
Yeah. In similarity search algorithms like k-nearest neighbors, k represents the total number of chunks the database is allowed to return. Vitally had his k-value set to k equals 3. He increased it to k equals 6.
So by changing that one integer, he's telling ChromaDB, don't just grab the top 3 pieces of the puzzle, reach deeper and grab the top 6.
Precisely. This simple change allows the database to pull all 3 of the fragmented pieces of that markdown list simultaneously.
Because they're all similar to the prompt.
Exactly, because they all share a high semantic similarity to the prompt, they will all make it into the top 6 results. Chroma grabs them all, hands them to the LLM in the context window, and the LLM can stitch them back together seamlessly in the final output.
It's amazing how these things that look like catastrophic AI failures are they're just tuning issues. The plumbing was just slightly too narrow.
Exactly.
Okay, so markdown lists are officially conquered. But Vitally is a developer, which means he doesn't just read lists. He reads code, and specifically, architecture diagrams.
And this brings us to a really fascinating challenge.
Oh, it does. He wants to vectorize .mmd files. These are raw Mermaid diagrams. And he also wants to ingest embedded Mermaid blocks that are sitting inside his Markdown files.
For listeners who might not be familiar with it, Mermaid is this brilliant Markdown-like syntax that generates charts, sequence diagrams, and flowcharts. It looks entirely like code.
Yeah, you'll see node definitions, arrows made of dashes, brackets.
Right. And this specific type of data is where we hit the absolute hard limits of standard embedding models.
Yeah, because he's using Hugging Face's all-minimal ML6v2 for his embeddings, which is a fantastic lightweight model for natural language.
It is. It's excellent for natural language. It understands nuance in prose, but it is terrible for raw technical notation.
Why is that?
Think about how semantic search models are trained. They are fed Wikipedia, Reddit, books, articles. They are trained to understand narrative.
Okay.
They fundamentally do not understand the spatial or logical meaning behind a string of text that looks like a bracket, auth, bracket, dash, dash, arrow, vertical bar, gRPC, vertical bar, B parenthesis, DB parenthesis.
Right. I'm trying to picture the semantic space we talked about earlier. So if I search for how does the login flow interact with the database, the embedding model puts that question in one part of the 3D grid.
Yes.
But the raw code for that process gets plotted somewhere completely different because it looks like a random string of punctuation.
That's exactly it. The mathematical coordinates of those code symbols don't align with human natural language.
It's like handing sheet music to someone who only understands lyrics. They can read the letters, they can see the notes on the page, but they have absolutely no idea what the melody is supposed to sound like.
That is a brilliant way to conceptualize it. The semantic distance is just too vast. The database will never match your natural language question to that raw code chunk.
So we can't just throw raw Mermaid code into ChromaDB and expect it to work. Let's dig into the code there because Vitally engineers an incredibly elegant fix for this.
He really does.
He builds what he calls a structural translation pipeline right inside his vectorizer.py script.
It is a masterclass in local AI orchestration. Vitally realizes he needs to bridge the gap between code and prose.
Okay.
So during the ingestion phase, when his Python script is first reading the files off the hard drive, he uses Python's built-in RE library regular expressions.
Regex.
Right, regex. He writes a regex pattern to scan the document and isolate just the raw Mermaid code blocks. He physically carves them out of the document text in the script's memory.
And then, instead of just throwing that raw code into ChromaDB and hoping for the best, he fires up his local Llama 3.1 in the background.
Entirely hidden from the user.
Right, before the user ever even asks a question.
Yes. He uses the Llama class in LangChain to establish a silent connection to the LLM. He feeds the raw Mermaid code to Llama with a highly specific system prompt.
What does the prompt say?
It says, you are an advanced system architecture interpreter. Analyze this raw Mermaid syntax and explain this exact workflow in clear, comprehensive technical sentences.
So he forces the AI to read the sheet music and write down the lyrics.
Exactly. The LLM translates the cold, hard relational syntax into a rich, plain text technical narrative. It outputs something like the authentication node connects to the database node using a gRPC protocol.
Okay, but if he just saves that summary, hasn't he lost the actual diagram? Like, if I want the AI to print the diagram later, how does it do it if we only save the summary?
And that is the masterstroke of this pipeline. He doesn't throw away the original code. He uses LangChain's document class to pack both things together.
How does that work?
The document class in LangChain has a core field called page_content. Vitally takes the AI's generated plain text narrative summary and puts it right at the top of the page_content.
Okay.
And then he pastes the exact raw Mermaid syntax directly underneath it, all inside the exact same vector chunk.
Hold on, why does putting them in the same chunk solve the problem?
Because of how embeddings are calculated. By putting the rich natural language summary in the exact same chunk as the code, the embedding model reads the summary and plots the entire chunk in the correct semantic location.
Oh, right next to concepts about authentication in databases.
Yes.
I see. So when you search for login flow, ChromaDB easily and mathematically matches your natural language question to the AI's plain text summary.
Right.
But because they are packed in the same chunk, when Chroma hands the data to Llama 3.1 to answer the user, the LLM is handed the summary and the exact raw Mermaid syntax along with it.
Precisely. The result is flawless. When you ask the system to recreate the diagram, or even modify, like asking it to add a new caching layer to the workflow, it executes with 100% accuracy because it's not guessing based on a summary.
It is looking right at the original source code provided in the context window.
Exactly.
It's beautiful. It
Yeah.
really is. It's like tricking the database into memorizing the code by attaching a story to it.
That's a great way to put it.
So we have the architecture diagrams perfectly memorized. But Vitally wants more. I mean, it's one thing for Llama 3.1 to print a nice mermaid diagram to the terminal screen. You can read it, but you can't really use it in another program without manually copying and pasting it. Vitally wants the AI to have hands. He wants it to physically save that diagram to his hard drive as a standalone file, like appmap.mmd, ready to be executed or shared.
This is a major leap in functionality. He's moving from a passive memory retrieval system, a system that just tells you things, to an active agentic workflow, a system that does things.
Which is the dream.
Absolutely. And to achieve this locally without relying on expensive cloud API tool calling features, he designs a custom tool interceptor layer directly in his terminal script.
Walk me through how you give a local LLM the ability to write to your operating system. Because out of the box, an LLM just generates text. It can't click Save As.
It can't. So you have to build a bridge between the text generation and the Python runtime. Vitally does this by adding a strict file export protocol to his system prompt.
Okay, what does he tell it?
He explicitly tells the AI, you have the ability to save files. If the user asks you to save a diagram or code, you must append a hidden, highly specific tag at the very end of your response.
That's the tag.
The tag he chose was bracket, write_file : filename.extension, close bracket, like write_file : filename.ext.
Okay.
And he instructed it to put the code it wants to save directly underneath that tag, encapsulated in standard markdown backticks.
Okay, I follow. And then the Python script that runs the terminal is constantly scanning the AI's output as it streams onto the screen.
Exactly.
So if Python sees that specific write_file tag, it intercepts the text, extracts the file name, creates a new file on the OS, pastes the code inside, and saves it. It's a brilliant workaround.
It is.
Except there's a bug. The script crashes.
A very frustrating bug, I imagine.
So what happened?
The LLM outputted the write_file tag perfectly and named the file correctly. But the Python script threw a massive parsing error and refused to save the file.
Why?
Because the LLM completely forgot to include the markdown backticks underneath the tag. It just left it blank. Or wrote plain text without the code block formatting.
But why would it do that? We explicitly told it in the prompt to use backticks.
Yeah.
Is the 8B model just, I don't know, not smart enough to follow multi-step formatting rules?
It's not an issue of intelligence. It's an issue of optimization. This is a very common behavior with highly optimized, instruction-tuned models.
I mean,
think about how the conversation flowed. The user asked, can you show me the architecture diagram and save it? The model, being helpful, printed the diagram earlier in its conversational response to the user.
oh, right.
Then, when it reached the end of its response and printed the write_file tag to trigger the save, it essentially calculated, I already provided this exact syntax 20 lines above, I'm not going to duplicate it here.
Ah, AI models are inherently lazy.
Yes.
Or, more accurately, they're trained to be hyper-efficient with their token generation.
Yeah.
If it already spent the computational power and the precious VRAM to type out the complex diagram once, it mathematically resists wasting power, typing it a second time in the same output.
It's like a teenager saying, I already told you that.
Exactly.
It is an efficiency mechanism deeply ingrained in the training data. The model wants to be concise. So trying to force the model to duplicate the code was fighting its fundamental nature. The fix required making the Python interceptor script much more robust.
So instead of yelling at the AI and the prompt to repeat itself, we make the script smarter. How did he upgrade it?
Vitally upgraded the regular expression logic in his interceptor. Instead of rigidly demanding that the code payload be immediately sequentially located under the tag, the script now adaptively scans the entire AI conversational response.
Looking for what?
Looking for the longest fenced code block it can find anywhere in the response.
It hunts for it. It sees the save tag, realizes it needs to save a file, and then looks back up through the chat to find the biggest piece of code.
Exactly. It uses the tag solely to get the target file name. Then it searches the whole output for the actual payload. Furthermore, to really tighten the behavior and ensure the AI at least formats the first diagram correctly, he updated the system prompt to explicitly demand the use of triple backticks under all circumstances whenever outputting code.
So between the stricter formatting prompt and the adaptive reject search, the file export protocol became completely bulletproof.
It did. It works perfectly now.
I love that. I love how half of this deep dive is just vitally learning how to communicate with the model's quirks.
Yeah.
It's like taming a very smart, very literal alien.
That's a very apt description.
Okay, let's move to the next evolution of this second brain.
Yeah.
Because Vitali realizes that a second brain isn't just about his local files on his hard drive. He wants external knowledge on demand.
Right.
He wants to type a command in his terminal, like Python vectorizer.py-u URL, and suck an entire Wikipedia page into his ChromaDB memory instantly.
Which is incredibly useful.
Yeah, and he tests this with a Wikipedia page to the Calgary Flames hockey team.
And traditionally, if a developer wants to pull web data into a RA pipeline, this is where they reach for heavy standard web scraping libraries.
Like Beautiful Soup or Selenium.
Right. But Beautiful Soup parses raw HTML, and HTML is a nightmare for vector databases.
Right, because you scrape a web page, you don't just get the article. You get the navigation menus, the footer, the click here to subscribe to our newsletter buttons.
The sidebar ads, the cookie consent pop-ups.
Yes, complete data pollution.
It absolutely ruins the semantic space of the vector database. If you ingest all that HTML and later ask the AI a question about hockey, the database might return the privacy policy of Wikipedia because the word rules was in both.
Oh, man. So how does he bypass the HTML nightmare?
Vitali had a real aha moment here. He bypassed raw HTML scraping entirely. He realized that Wikipedia, like many modern platforms, offers an official REST API content endpoint.
Okay, I want to make sure everyone listening follows this. What is the fundamental difference between scraping the web and hitting a REST API?
Think of scraping like taking a photograph of a restaurant menu that is covered in ads and trying to read the text off the photo. Hitting a REST API is like going into the restaurant's kitchen and asking the chef directly for the ingredient list. The API endpoint is designed for machines to talk to machines. It bypasses the visual web page entirely and asks Wikipedia's database directly for the raw underlying text data.
And he does this using Python's built-in erlib.request library. So no heavy dependencies, no complex HTML parsers.
Exactly. It is incredibly lightweight. The API returns clean, highly structured JSON data that contains the article text natively.
So there's no noise.
None. No sidebars, no menus. The vector database remains pristine, and the ingestion script maps it perfectly as a standard text document, tagging it with doc_type:\md.
It's so much faster and cleaner.
Okay.
Okay, we have conquered Markdown. We have tamed Mermaid. We are pulling from Wikipedia APIs. But now we have arrived at the final boss.
The big one.
The absolute bane of RL pipelines everywhere.
Yeah.
Excel spreadsheets. Vitali wants to vectorize .xlsx and .xls files, and this is where everything nearly fell apart.
Tabular data is incredibly hostile to the way Large language models and vector databases process information.
Why is it so hard?
Well, Venly uses the Pandas library, which is a powerhouse for data manipulation, and OpenPixel to read the complex XML structures of the Excel files. That part is standard. But his first failure was relying on our old friend, the standard chunking strategy.
The recursive character text splitter.
Mhm.
But why does a text splitter destroy a spreadsheet?
Because of how humans read tables versus how algorithms split them. Imagine an Excel sheet. You have column headers at the very top. Project name, VRAM target, power cap.
Right.
Underneath, you have hundreds of rows of data. If you blindly chop that document every 512 characters, row 10 gets completely physically separated from the column headers in row 1.
Oh, I see. So the LLM receives a chunk of text that just says 54, 12, 8.
Exactly, which is completely meaningless without the column headers. It's just random numbers floating in the void. The AI has no idea if 12 is the VRAM target, the power cap, or the project ID.
That makes total sense. So Vitali sees this total loss of context, and he tries a new approach. Failure number 2, micromatrix splitting.
His logic here was actually quite sound conceptually. He thought, if the problem is losing the headers, I will use pandas to extract the header row. Then I will iterate through the spreadsheet and I will paste those exact headers onto every single row individually.
Oh.
Yeah, I will create a self-contained mini markdown table for every single row in the spreadsheet.
But wait, that makes logical sense. Row 2 becomes its own document with headers. Row 5 becomes its own document with headers. Every row is perfectly contextualized. Why is this a failure?
Because it led to utter catastrophic database fragmentation. We have to remember how ChromaDB limits returns. When you do a similarity search, Chroma only returns the top K results.
Right, we talked about K-value earlier.
Furthermore, the embedding model itself has silent token clipping limits, usually around 256 to 384 tokens before it just stops reading the junk.
So if you search for, tell me about the memory requirements for all projects, what happens?
Chroma pulls row 2, maybe row 5, and completely ignores the other 98 rows of the spreadsheet because they couldn't all fit into the top K results.
Wow.
It hands this deeply fragmented mess to Llama 3.1.
And the model hallucinated hard. It confidently lied to Vitali. It told him that a project called Project Aether had more than 10 gigabytes of VRAM when the spreadsheet clearly stated it only had 8.
Yep.
We over-engineered it. We sliced data so thin and created so many microdocuments that the AI entirely lost the plot.
It is the librarian handing you a diary problem all over again, but this time it's much worse. The librarian is handing you single, torn-out pages from a dictionary and asking you to write a comprehensive novel.
The data is technically there, but the structure is obliterated.
Exactly. The solution required taking a massive step back, a technique we can call header-locked direct injection.
Wait, direct injection. Are we bypassing the text splitter entirely?
Completely. Vitali used pandas to convert the entire Excel sheet into a single, massive, unbroken markdown table in memory. And then he didn't use the recursive character text splitter at all. He took the entire formatted table and ingested it directly into ChromaDB as one giant, single contextual chunk.
Hold on. Doesn't that completely violate the token limits you just warned us about? Won't ChromaDB choke on a chunk that big?
It's a balancing act. It can choke if the spreadsheet is 10,000 rows long and exceeds the absolute maximum token limits of the specific embedding model. But for standard project spreadsheets tracking a few dozen or 100 rows, modern embedding models can handle it.
Okay.
By mapping it as a single chunk, it ensures that when Chroma pulls it for relevance, the LLM receives the entire context window, every single row, every column, all perfectly aligned in one unbroken view.
Okay, so the whole table is finally perfectly intact in the AI's context window.
Yeah.
The headers are there, the rows are there. Vitali asks the AI a simple mathematical question. List all projects from the spreadsheet with greater than 10 gigabytes of VRAM.
A very simple query.
Super simple. And the AI goes through the list. It looks at a project named Project Kronos, which clearly has 12 gigabytes listed. It literally writes down in its thought process, Project Kronos, 12 GB.
But then...
Right, but then when it outputs the final answer list to the user, it just says Vulcan and Horizon. It dropped Kronos. It completely left it off the final list.
And this brings us to perhaps the most profound lesson in this entire deep dive. This is not a database error. The data was injected perfectly. The AI saw the data perfectly.
So what happened?
This is a classic small model quantization flaw combined with reasoning fatigue.
Let's break that down. It literally looked at the math, saw that 12 is greater than 10, acknowledged it, and then got the final answer wrong. Why?
To understand this, we have to look at the system prompt. Vitally had instructed his 8B model, the very core system instructions, to be a polite, helpful assistant.
Okay, standard stuff.
Now, you have to understand how an LLM generates text. It is not a calculator. It is a probability engine predicting the next word based on attention weights.
Right, it's guessing what word comes next based on the rules we gave it.
Exactly. When an 8 billion parameter model, which is already heavily compressed or quantized to fit into 8 GB of VRAM, making its logical pathways slightly fuzzy, is told to be conversational and polite, its attention weights physically shift.
Wait, really?
Yes, it prioritizes predicting conversational prose, friendly greetings, and flowing language over strict, rigid mathematical operators. By the time it read down to the bottom of the table to evaluate Project Kronos, it suffered reasoning fatigue.
Oh, wow.
The polite assistant persona overpowered the mathematician. It lost its mathematical focus.
That is wild to think about. The friendly personality we gave the AI actually made it worse at basic math. We told it to be a host, so it forgot how to be an accountant.
That's a perfect analogy.
So how did he triumph over this? Does he just need a bigger model?
He doesn't need a bigger model. He realized that the prompt decides everything. He went into vector-terminal.py and completely rewrote the system prompt identity.
What did he change it to?
He ruthlessly stripped away the polite assistant persona. He gave Llama 3.1 a new identity. You are a deterministic data validator engine.
Oh, wow. You are a precise data parser. You do not make conversation.
Exactly. But he went one step further. He enforced a chain-of-thought mathematical processing rule. He explicitly demanded in the prompt that the LLM evaluate every single row sequentially and type out its logic before giving the final answer.
Like a scratch pad.
Exactly. He forced it to output literal scratchpad tokens like Project A:8 greater than 10 : no, Project Kronos 12 greater than 10 : yes.
He forced it to show its work, just like a math teacher making you write out the steps so you don't make a careless error.
Precisely. By forcing the model to generate the actual textual tokens that represent the mathematical logic before generating the final summary, he activated the model's internal reasoning weights.
Because it reads its own output.
Right. The generated text acts as an anchor for the next prediction. The result was flawless execution. The model mathematically proved 12 greater than 10 : yes on the scratchpad, and because that yes was now in its immediate context window, it successfully outputted the perfect, complete list.
I'm trying to wrap my head around this, because that is a massive realization for anyone building with AI. Prompt engineering isn't just about getting the right tone of voice. It's about physically rerouting how the model allocates its computational probability.
It really is.
By changing a few words, you can turn a hallucinating, terrible mathematician into a flawless logic engine. That's incredible.
It's the difference between a toy and a tool.
Exactly. So we've built this incredible system. Vitali's engine reads Mermaid architecture. It digests raw Wikipedia APIs. It understands complex Excel matrices. It physically exports files to the OS. It is a true second brain. But there's one last piece of housekeeping.
Right, cleanup.
Because a brain needs to forget, too. What happens when you want to delete something? Let's say you accidentally upload a file with an AWS password in it. Or you just want to clear out embarrassing old chat logs where you asked the AI stupid questions. How do you delete that without corrupting the whole Chroma database?
In many basic tutorials, you can't. Usually you need a complex external indexing tool, or you just have to wipe the whole database and start over.
Which is a nightmare if you have hundreds of documents.
Exactly. But Vitally leverages the fact that LangChain's Chroma integration natively supports conditional matching, specifically the where dictionary queries.
Right, tying back to the metadata sticky notes we talked about in the very beginning.
Precisely. He creates a standalone utility script called replace_data.py. Because he engineered the ingestion, perfectly remember, every single chunk of text in his database has a source_file tag or a source:_user_history tag. He can write a Python script that simply says to Chroma, execute a delete operation where the source equals user_history.
Boom! All chat history wiped instantly. But the markdown documents and the Excel sheets are completely untouched and safe.
Exactly. Or for the password scenario, he can use a semantic search to find the exact specific chunk containing the leaked password phrase.
Oh, that's smart.
He extracts its internal database UUID and purges only that specific chunk from memory. It gives him absolute surgical control over his second brain without ever touching the core document structure.
This has been an absolute journey. Let's summarize what we've explored today. Vitali's setup started as a basic, buggy text reader. It is now a production-grade, privacy-first, local Agentic.
It's a beast.
And it runs entirely on consumer hardware, an AMD Ryzen AI 9 and an RTX 4060 laptop GPU, pushing a highly efficient 37.69 tokens per second. It handles subtitles, it parses complex markdown files without fragmenting, it translates raw Mermaid architecture diagrams into technical prose for the AI to understand, and it ingests Excel matrices flawlessly. It even has hands, it writes files directly to the hard drive.
It is a remarkable testament to the power of local AI. It proves that you don't need a massive data center if you properly align the ingestion architecture with the generation logic of the model.
Now, before we leave you, we want to say a huge thank you for joining us on this deep dive. We would be so grateful if you would subscribe to the channel RA to Riches AI on YouTube, where this deep dive is released.
And please leave a like on this and other videos on the channel to help us keep bringing you these deep dives.
Yeah, please do.
And if I can leave you with one final, broader thought to consider today, we saw how simply changing a system prompts persona from a polite assistant to a deterministic data validator instantly cured an 8B model's inability to do basic math.
It cured its hallucination.
Exactly. It makes you wonder, what other artificial limitations are we currently accepting from the AI tools we use every single day, simply because we haven't asked them to act differently?
Are we staring at a muddy X-ray, assuming the machine is broken, when all we really need to do is recalibrate the lens? Think about that. We will see you next time.